All right, first, a couple of things that came up yesterday. So first of all, if I haven't mentioned it enough, if you're learning in a US institution, you're eligible to get Magma for free. You're eligible to get the latest version. This is the generous contribution of the Simons Foundation. So you can insist against your IT or your college that you're eligible to get Magma and they should give it to you. If you run into trouble, you can always contact Magma directly. And if you have some other issues, I posted a link to the GitHub repo of Magma online. You can raise an issue there. All right. Another thing just about the problem sets that you got yesterday. There were many interesting things coming up there. And if you want to learn more, just come and ask me. I'm here to elaborate and answer your questions. And last thing, there are a lot of terms that I'm saying and you might not understand yet or not know them. Feel free to stop me, ask me about them. And also, you'll see some of them in the course of the week. They relate to the other mini courses. So no worries, you can ask probably any one of us about all these terms. All right, so yesterday we talked about lattices and quadratic forms. And today we're going to focus on number fields and related to the Kronecker-Weber theorem that you're proving in Laurie's mini course. So we're going to see how Magma and the LMFDB can help us with number fields. So first I'll briefly talk about number fields and their invariants. Some of them will just be a review. And then I'll talk a little bit about abelian extensions and the relation to Kronecker-Weber. And in what's left of the talk, I'll talk about class groups, unit groups, and something called the Cohen-Lenstra heuristics that I'll explain more once we get to, which is an active area of research for which computational tools are very useful. And of course, we'll finish by seeing the LMFDB in action. So you've already seen what is a number field. It's just a finite extension of the rational numbers. And you've seen some examples like quadratic fields or cyclotomic fields. The first invariants that we'll care about in number fields, first of all, are the ring of integers. These are really just all the elements that are integral. And I'll remind you that integral means that they satisfy a monic polynomial with integer coefficients. There's the signature of the field. This is the number of embeddings that it has into the real or the complex numbers. And there's a fundamental invariant that is the discriminant of the ring of integers. I'll explain in just a moment what that is. Okay, so if you think about the ring of integers of some number field, then it is a lattice in the sense of yesterday. It's just a Z module, right? An abelian group. If you add two such integers, they're also integers, right? And it has a natural quadratic form or bilinear form coming from the trace. So you can multiply integers and take the trace. This is symmetric, it's bilinear, and it gives you a nice quadratic form. And the discriminant of this lattice with this quadratic form is the discriminant of the ring of integers. Maybe a quick example. If you take the quadratic field q square root d, where d is square free, then there are famously two cases of what the ring of integers is. When d is 1 mod 4, say 5, then 1 plus square root d over 2 is integral. It's not too difficult to see. And if not, then you're just left with 1 and square root d spanning your lattice. And you can write the Gram matrix of this symmetric bilinear form in each case. In the first case, 1 and square root of d, the trace of square root of d is just 0. So you're really left with the diagonal matrix. And in the second case, you get trace 1 for the 1 plus square root d over 2. you get this nice matrix of determinant D. So you see that the discriminant is either 4D or D respectively. Okay, we will use a famous theorem that tells us that a prime ramifies in the ring of integers if and only if it divides the discriminant. So by now, some of you may not even know what it means to ramify. But as Laurie said before, in number fields, there's a notion that generalizes the notion of unique factorization of primes called ideals. So we do have, in some sense, unique factorization of ideals in number fields. And one can ask, what's the factorization of the ideal generated by an irrational prime P? If this factorization is a perfect power, say P is a square, then we say that it ramifies. Okay. Okay, the example that I want to choose to do some Magma computations today will be a cubic field. We'll take the cubic field of discriminant minus 23. You can represent it by an element who's the root of x cubed minus x minus 1. And maybe I'll just briefly do what I always do and open a Magma terminal and show you how some things work. You can also ask me, or we can try to do other things than what's just written on the slides. You all have the slides you can follow on your own time. And that didn't work as expected. Okay. Maybe I'll skip the live demo for now. Sorry, some technical difficulties. Anyway, you can see that Magma has a natural interface for constructing this number field, constructing the ring of integers, computing the discriminant, computing the signature, and it can also compute some other invariants that we will encounter later in this talk, like the class number. Okay, why did I choose this field? So first of all, this is the cubic field with the smallest discriminant. So quadratic fields you see all the time. So I wanted to choose something more interesting. But more importantly, quadratic fields are always abelian, and this is an example of a non-abelian field. So if you look at the Galois closure, it has a non-abelian Galois group, S3, just like the Q with a joint cube root of 2 that you saw earlier. So Kronecker-Weber doesn't apply directly to this field. I attached here its LMFDB label, so you can just click and see it on the LMFDB. And this field will also reappear somewhat surprisingly at the end of the lecture. Okay. Now, you could ask, well, I told you about this factorization of primes in this in number fields in general. And you can ask, how do primes factor in this number field? And Magma also allows us to do this. So here I just sampled a bunch of primes. So you can start, say, by 2, 3, 5, and see how they factor. So, for example, if you see what's written here, for every prime, I wrote down the norm of each of the prime factors in this cubic field. So, say in the first case, where you see p equals 2, there's only one prime. So it means that the ideal generated by 2 is just a prime ideal. And the factorization just includes this one prime. and this prime has norm 8. That's like 2 cubed. That makes sense because the extension is of degree 3. And similarly, the same thing happens for the prime 3. For 5, you already see that there's more than one prime. And this is a situation where we say that the prime is split. And in this case, it's only partially split. It could split up to 3 factors in general in this cubic extension. And here it's only split into 2. And you can see in the case of p equals 23, which is a prime dividing the discriminant. Remember, I told you in this case we say that the prime ramifies. And indeed, we see that one of the prime factors appears with a power greater than 1, like a square. And p equals 59 is here to demonstrate a different behavior where the prime is totally split. So there are 3 prime ideals in this factorization. And by doing some math, one can see that this splitting of primes in a number field relates to how this polynomial actually splits when you reduce it modulo p, at least for primes not dividing the determinant. Okay, so we can do all these things computationally. How does it relate to abelian extensions, which is the topic of your other mini course? So in our cubic example, we saw that this splitting of primes is governed by how this polynomial x cubed minus x minus 1 splits when you reduce it modulo a prime. But for abelian extensions, you can say something more. The splitting of the prime, the way that it factors into prime ideals, actually depends only on p modulo some integer. You only care what is the residue that p leaves with respect to a certain integer, which we call the conductor. So this simplification is basically what Kronecker-Weber tells us. So you've already seen this in Laurie's talk, that every abelian extension of Q is a subfield of a cyclotomic extension. And it means that if you have some abelian extension or you want to understand the abelian extensions, it's enough to look at the cyclotomic towers. And you've already seen some of these examples. They shouldn't be new to you. And maybe the interesting question that one should ask is, given an abelian extension, what is the smallest n for which it is contained in a cyclotomic field, Q zeta n? And this n is what is known as the conductor. So I gave you 2 different ways of seeing what the conductor is. Okay. Now, this property of the conductor, of being depending only on the residue of the prime p modulo some integer, is coming from the fact that for abelian extension, there's some unique element for unramified primes called the Frobenius element in the Galois group. And a famous theorem called Artin's reciprocity theorem states much more than this, but what we will take from it is that if we have an abelian extension, then this smallest integer that we specified earlier, this conductor, actually defines how this Frobenius element acts. So there's some smallest integer, the conductor of our field, that tells us how a particular element of the Galois group acts. So if we revisit Kronecker-Weber, what it tells us is that our field is contained in a cyclotomic field if and only if its conductor divides n, where n is the order of the root of unity. So the fact that these 2 definitions of conductor agree is a major part of the content of Kronecker-Weber. Now, just to exemplify with two simple examples, well, what is the conductor of a cyclotomic field? If we have the cyclotomic field Q zeta n, the conductor is naturally n, right? That's the smallest cyclotomic field it's contained in. Of course, one should be a little careful here because, for example, Q zeta 3 and Q zeta 6 are the same field, right? Or like, what is Q zeta 2? So that's why we have here n is not congruent to 2 mod 4. And there's the example of quadratic fields. So remember, we looked earlier at quadratic fields, and we saw their discriminant is either d or 4d. And the Galois group is just plus minus 1, definitely abelian. And in this case, the Frobenius element is determined by the Kronecker symbol. So you really just care if this discriminant is a square or not a square modulo p. And the conductor is, again, just this discriminant. So maybe if you want to take away something from this discussion, is that the conductor is the smallest modulus at which the splitting behavior of primes depends on the residue classes. Okay. You can also do explicit Kronecker-Weber in Magma. So in this case, you start with some abstract field. Just define a field, again, a cubic field with some other innocuously looking polynomial, just met across the whole. You define the number field, you compute the discriminant. Okay, you check if it's abelian. So far, so good. Well, if it's abelian, then it should be contained in some cyclotomic extension. How do we figure out which? Well, we compute the conductor. So this is computationally possible. And you have to tweak a little bit the Magma code. So for this field, so at the moment you have a field, you want to make it into a structure known as an abelian extension. The point is that you can define a abelian extension without actually specifying a unique polynomial that defines the number field and do all the computations in the number field and vice versa. So it's convenient to have these two structures in different locations. But once you made it into an abelian extension, then you can compute its conductor. And the reason I inserted the word minimum here is that the conductor is given as an ideal, and it will just take too much space on the slide. So I took the minimum element of this ideal. Now, we know that the conductor predicts where our field will lie, right? In which cyclotomic extension. So now that we know the conductor is 7, we know this field can be embedded in Q zeta 7. So we can explicitly construct the cyclotomic field and check if our field embeds there. So if it's a subfield. And in fact, one can see pretty easily that here the embedding just sends the root of this cubic polynomial into zeta 7 plus zeta 7 inverse. As one would expect, as this field is the real subfield of Q zeta 7. So this is a version of the Gauss sum. Right? You were looking at Gauss sums and how they help you embed the quadratic fields inside the cyclotomic field. So the same thing happens here, where 1 and minus 1 is are the coset representatives that we're summing over here. Because this time we're degree 3. Okay. Yeah. So what happens beyond the abelian case? So we had our running cubic from before, which is not abelian. We can try to find its Galois group. For example, we can construct the normal closure. We can look at the Galois group of this normal closure and see that it has 6 elements, and even further see that it's isomorphic to S3. We can also look at the discriminant of the ring of integers of this field and see that it's minus 23. So if you use the fundamental theorem of Galois correspondence, you will see after a little work that it's not surprising that L is actually the extension of K by this square root of minus 23. All right. So maybe the last thing I want to point out, well, in this extension, in this normal closure, maybe I'll show you on the board. It's very similar to a picture you've already seen before, but we have here this degree 3 extension of Q, and we have here this normal closure, which is actually K adjoint square root minus 23. So it also has this Q adjoint square root minus 23 inside, which is a quadratic extension of Q. And this K is not Galois, so there will be other extensions right here. Degree 3. But this one will be the only abelian extension we see here. All right. So Kronecker-Weber can be generalized to imaginary quadratic base fields. This is something that Kronecker thought about already, and it's known as Kronecker's Jugendtraum, and it will come up tomorrow and also in the rest of Laurie's talks, I think. He'll touch upon it. Where instead of roots of unity, you find some other way to produce what will be a general abelian extension for imaginary quadratic fields. Questions so far? Okay, so we've seen how we can use Magma to compute things about number fields, to compute conductors, to check embeddings of number fields into others, to look into Galois groups. And the next thing I want to talk about is some other more advanced invariants of number fields that we care about and how we can do some research with them. So maybe one of the most researched invariants of number fields is the class group. So the class group is an invariant coming again from this structure of ideals in our number field. So I talked earlier about how one can generate an ideal by a single element. So these ideals are known as principal ideals. And these are denoted here as pk. But if you look at all the ideals, and you also allow fractional ideals, so you allow, if you have some ideal, you can divide it by some number or multiply it by some rational element, then you get a group. So these ideals can be multiplied, and this group is abelian because multiplication of ideals is commutative. I think the most interesting part is to show that there's an inverse, but that happens to be the case for the rings of integers of number fields. And that way you get an abelian group. And if you quotient out by these principal ideals, you get the obstruction for ideals to be principal. So if you're interested, for example, in unique factorization, and you know that you have unique factorization of ideals, then having all ideals principal is very convenient. Then you almost have unique factorization for elements. So because we were interested in studying or quantifying this difference, how non-principal are we? We're interested in this quotient, this class group. And maybe a an important theorem here by Minkowski is that this class group is finite. So this is really a finite group, and its order is known as the class number. Another major theorem tells us about the structure of the unit group of the field. This is Dirichlet's unit theorem. So again, these two major theorems of Minkowski and Dirichlet are the major theorems of almost every course in algebraic number theory. And it tells us exactly how the group of units, right, the invertible elements in the ring of integers, behaves. So this is a finitely generated abelian group, but we can tell exactly its structure given just the signature of the field. Maybe some examples to see how these things play out, or what are these invariants. So if we're looking at Q adjoint I, right, then the ring of integers is just the Gaussian integers. The class number is 1. It's a principal ideal domain. And the unit group is mu4, so all the roots of unity of order 4, plus minus I, plus minus 1. Note that it tells you that you have unique factorization up to one of these 4 elements. Right? Same as in the integers, you have unique factorization up to plus minus 1. On the other hand, if you go, for example, to Q squared root minus 5, then the class number is 2. One can find one can show that there's no unique factorization quite easily, but one can also find ideals that are not principal. And further, well, I mean, here it's obvious if the class number is 2, then the class group has to be Z mod 2. And if you'll recall the 2 quadratic forms that we saw yesterday, so these could be seen as representing this particular class number. The idea is that we have each of these ideals is a 2-dimensional lattice over Z, right? Our number field is a quadratic number field, so its dimension over Q is just 2. So if we have any ideal, it's just a 2-dimensional lattice, and the norm gives us a quadratic form on this lattice. So given 2 different lattices, say one of them principal and one of them not principal, we can look at the norm forms. And these norm forms that we see here, for example, x squared plus 5y squared is the norm form on the ring of integers, and the other quadratic form is the norm form on a non-principal ideal. And these are representing the 2 classes of ideals. So these are the 2 binary forms of discriminant minus 20 that you saw yesterday that belong to the same genus but are not isometric. If you go further to something like Q squared minus 21, you'll see that the class group contains more information than just the class number, because the class number is 4, but the class group actually tells you that this is Z mod 2 cross Z mod 2 and not a cyclic group of order 4. Now, in all these cases, these were quadratic imaginary fields, so the unit group was always pretty small. But if you go to real quadratic fields like Q squared root 2, you will see by Dirichlet's unit theorem that there's also a non-trivial rank, in this case rank 1 for the unit group. So although in this case the class number is 1, we still have an infinite unit group generated by 1 plus square root 2, which is a little annoying if you're looking for, say, unique factorization of elements. Okay. And of course, as always, Magma can help you compute these things. Here's an example where you take the quadratic field Q squared minus 23. You can compute the class group, see that it's of order 3. You can do more than just compute the class group. You see, when I call here class group, it returns 2 things. It returns the group, and it returns another thing that I called phi, because it is just a map. So C is like an abstract group, but the map phi allows me to relate elements of this group to actual ideals and vice versa. So if I have an ideal, I can check which element of the class group is it. So for example, here I loop over the generators of a certain ideal. This ideal is the image of the generator of C. So C.1 is a generator of this group. I apply phi, I get an ideal. And when I get this ideal, I can look at its generators. And I wanted to show them as elements of K. Because a priori, when I have these generators, they will be represented as elements of the ring of integers. And I wanted you to see them exactly as elements of the field. And you see that these two generators are 2 and half times square root minus 23 plus 1. So these are actually the generators of this ideal that generates this class group. So it's a non-principal ideal that if you raise it to the third power, I cubed will give you a principal ideal. Other than class groups, we can also compute unit groups. And here I give the example of q square root 2 that we talked about earlier. Again, the unit group will give you an abstract group, but you can also get a map between this abstract group and the actual ring of integers that will get you these units. So here I run over the generators of this unit group, and for each one of them, I look at its image. And again, I show it as an element of the field. And you can see here 1 minus square root 2, which is the inverse of 1 plus square root 2 from before, and minus 1, generating the torsion part. OK. Yeah, maybe the last thing I want to say about this seems like instantaneous, especially when I do it with small examples. But as the fields get large, these get more complicated, and these algorithms, like the best state-of-the-art known algorithms for computing these things like class group and unit groups are sub-exponential. So they can be notoriously difficult for general number fields if the degree is large or the discriminant is large. Okay, this leads us to the next step of trying to figure out how these class groups or class numbers behave. And this is a very difficult question. Even the simplest question that one can ask is very difficult here. And you can see this by the fact that a simple question that Gauss raised in 1801 is still an open problem, and we have made very little progress towards it. And it's a very simple conjecture. Just there are infinitely many real quadratic fields with class number 1. It seems plausible, but we have no proof. Now, maybe the most significant step in this direction was made by Cohen and Lenstra, where they gave a much stronger prediction than Gauss. So instead of just stating that there are infinitely many, one can ask, how many are there? Right? This is something more precise, and maybe will lead to better understanding. And their prediction is that the class group should behave like a random Abelian group, more or less, or at least the odd part, which would mean that it's weighted inversely proportional to the number of symmetries that it has, number of automorphisms. So if you just like run into a group in the wild, that's the chances of encountering one such group. And if you follow this idea and try to just see how many real quadratic fields are there with class number 1, then you run into this computation. Here you just sieve over all p parts of the class group and ask, okay, I want each of them to be just trivial. And you're getting this proportion of 75%. And the question is, can we test this conjecture? And nowadays, it's very easy to test such conjectures. I should say that Cohen lens tree heuristics are largely open. It's an active area of research. There are some averaged versions that were proven, but in general, if you're able to make any progress on Cohen lens tree conjecture for some particular case, it's usually interesting. Okay, but how can we do that? So here's an example. You choose some bound that's not too small, because as we'll see, convergence is slow for these things. But say take the bound to be 1,000,000. And let's restrict primes that are 1 mod 4 for simplicity, and just compute the class numbers. Okay, so Magma gives us the interface to just compute the class number. Class number of P is just the class number of Q square root P, or more generally. And this multiplicity function just counts the number of occurrences of an element, as you would expect. And the reason I multiply by 1.0 in the end is because naturally, when I divide the two integers in Magma, it will give me a rational number, and I really want to see it as a real number. So this multiplication just converts it into a real number really quickly. As you can see, it's getting close to 75%, but not that close. There's still a 3% gap. And you can ask, okay, but maybe if I'll go far enough, if I'll go to 10 to the 9th, maybe I'll see it happening. So maybe the right thing to do is to look at the graph of how this behaves, right? How these ratios behave. So you can really form the ratios. Here I just created a one-line function that for every n counts this, computes this ratio of the number of class number 1 divided by the total number of class numbers, and computed it for all n's from 1 to 1,000,000. And then you get some points, and you just need to plot these points. So Magma doesn't provide its own plotting interface, but you can put this number in a file and use your favorite thing to plot them, either MATLAB or SVG or any online, I don't know, Cosmos, whatever you like. This is what I get from plotting these numbers that were produced by the script you just saw. So here in the x-axis we have the primes, and the y-axis is the ratios. It shows you that it's descending quite fast at first, and then slowly, gradually continues to descend. So as I said earlier, we conjecture like 75%, and going up to 1,000,000, we only see something like 78%. So we could go up to, I don't know, 10 to the 9th or even more, but it will, like, as I said, computing class numbers is a sub-exponential algorithm. It gets more difficult as the discriminants increase. And that's where the LMFDB comes in. So people have already computed these class numbers, and you can find them on the LMFDB. So here I give an example where we just query the LMFDB directly. Instead of going online to the interface you saw yesterday, where I can browse and filter and check for what I want, I can do it programmatically through an API that the LMFDB provides. Basically, they're just SQL tables, but you can also access them from Sage or Python, which is very convenient. And it has already computed class numbers to a much larger extent. Actually, the LMFDB also has some external tables with class numbers up to higher discriminants, but for now this will suffice. So here I use the Sage version. So if you go to the LMFDB GitHub repo, you can download it, and there are instructions how to install this. There's also a version, if you don't have Sage on your computer, you can download LMFDB Lite, which just works from Python. And then you can see that I can format a query to the database. This query is just a dictionary, where for each field, I give the value that I want. For example, here we're interested in quadratic field, so the degree has to be 2. I want them to be real. So in the signature, there's R1, the number of real embeddings, and R2, the number of complex embeddings. So I just ask that the number of complex embeddings will be 0. So that would make it a real quadratic field. The reason for the number of ramified primes to be 1 is just because we're interested in Q square root P, where P is 1 mod 4, so the discriminant is P. Okay. And the absolute discriminant, I ask it not to be 8. So this is really just primes that are 1 mod 4 and not, say, P equals 2. Okay. And then you see that one can access this database, db.nf fields. So db is just the general access point to all the database, and then you can choose the table. As you saw earlier, there's lattices, there are other stuff, elliptic curves, modular forms, and here we're just accessing the number fields, and we're just looking for all the things that this query returns. And the last two things you will see here is that I only take from the database these two fields, the absolute discriminant and the class number. So there are many fields for each such number field, many interesting information that the LMFDB stores. Right now, we don't care about any of these. We just want the class numbers. We want to sort them by discriminant. And so if I'm just looking at the class numbers, I can again check for this ratio and see that if we go up to 10 to the 8th, we get 77.7, which is slightly better than what we got when we went up to 10 to the 6th. So it really continues to descend. But as you see, convergence is still very slow compared to the 75.45 that we expect. And here's the graph that one gets from plotting this data from the LMFDB. All right, questions? Yes?
I have a question about, is it possible, so before, not in the section about, let's see, about you connecting Gala groups to, not Gala, sorry, the class group to quadratic forms, is it possible to say anything more about that?
Yes, I mean, this is something Gauss already did. So, I mean, this can be made very exact. So here, the class sets of quadratic forms are in bijection with classes of ideals in number field, and you can match the invariants one to the other. You can see it, you can read about it in many standard number theory books. I would recommend, because I like the computational perspective, Cohen's book, A Course in Computational Number Theory. All right, yeah.
What do you mean exactly by the class group should be like a random union group? Is that a heuristic?
Yeah, that's the heuristic. I mean, okay, the P part of the class group for every odd P should behave like a random abelian group. At 2, like, there's something different that's happening, like the genus really determines how this behaves. Yeah. So we saw that there's a very slow convergence for Cohen-Lenstra. And that's why this conjecture is hard, and even verifying it is hard. Not talking about an actual proof. And as you've noticed, the original problem of Gauss also still remains open. We can't even prove that there are infinitely many real quadratic fields with class number 1. So in the last 5 minutes of this talk, I'm going to talk a little bit about Hilbert class fields and about the LMFDB. So for a number field K, one can talk about the maximal unramified abelian extension. So this is an abelian extension where no prime is ramified. So for example, if you start with just Q, the rational numbers, there is no unramified extension of Q. That's an interesting fact. It might seem trivial, but it is interesting. And so Q is just a Hilbert class field of itself. But if you're looking at, say, Q square root 5, then suddenly there is an unramified abelian extension of Q square root 5. If you just adjoin I, like the square root of -1, you get you get an unramified abelian extension. And the maximal such is called the Hilbert class field. And a more advanced topic known as class field theory that's coming from many of the ideas that we talked about before by Artin tells you that the Galois group of this extension is isomorphic to the class group of the field. So here's an example. If you start with the quadratic field square root -23, we looked at before, and you compute its Hilbert class field, you get some field of degree 6. Notice that Magma a priori gives us this field as an extension of K, so as a relative field. So if you want to look at it as an extension of Q, then we needed to change it to the absolute field. This is this H abs. And one can compute its discriminant, for example, and see that it's -23 cubed, which is not a coincidence. But more interestingly, one can see that this field is isomorphic to extending Q squared -23 by x cubed minus x minus 1. So this field L that we had here is the Hilbert class field of Q squared -23. This cubic extension of Q squared -23, notice that the Galois group of this extension is Z mod 3, is isomorphic to the Galois group, not to the Galois group, sorry, to the class group of Q square root -23. All right. So one can also construct this Hilbert class field using an analytic recipe, same as for abelian extensions of Q. We could construct them by just adjoining roots of unity, these zeta n's, and having cyclotomic extensions. Here one can construct these Hilbert class fields by adjoining values of some other function, some function known as the J function, where you take some complex numbers that are known as CM points. So this is something related to elliptic curves. If you're looking at an elliptic curve represented by a lattice, this lattice has a basis where one of the basis elements is 1, and the other is a complex point in the upper half plane. This is this tau here. And if this elliptic curve has has more endomorphisms than usual. So you can always multiply points on the elliptic curve. It gives you natural endomorphism, maps from the elliptic curve to itself that preserve the group structure. But if you have more than that, for example, you have, say, multiplication by something like square root of minus 23 in your lattice. An easy example would be take the complex numbers and quotient them by the ring of integers of this field. You'll get naturally an action by square root of minus 23. Then you have more endomorphism than you would expect. And when you have these situations with extra endomorphisms, we call these elliptic curves CM elliptic curves. So they have complex multiplication by some complex element, not just integers. Anyway, the point is that by evaluating this J function at CM points, one can obtain these Hilbert class fields, and the minimal polynomial of these values is what is known as the Hilbert class polynomial that can be made explicit using elliptic curves. So here are some examples for sample queries one can do with the LMFDB. You can ask for the smallest degree 5 field with a certain Galois group. You can ask for all the number fields with a certain class group sorted by discriminant. You can order them by Galois group, discriminant, and ramification type. And you can also go from number fields to different things that are in the LMFDB, like Galois representations, L functions, or modular forms. So just now there is a workshop working on something called Malay's conjecture, which is very similar to the Cohen-Lenstra heuristics in the sense that it's about the distribution of Galois groups instead of class groups, distribution of Galois groups of number fields extensions, and it predicts how these distribute. And there they use heavily these properties of the LMFDB, where you can just query for different different queries and filter according to different criteria. Maybe another thing you can see on the LMFDB relates to the shape of the number field. So in a similar way that we talked about the theta series associated to a lattice, one can form a zeta series for every number field called Dedekind zeta series. It corresponds to the Riemann zeta function, but for number fields. And one can ask if two number fields have the same zeta function, what does it say about them? Do they have to be the same, for example? And there are examples of non-isomorphic number fields with the same zeta function, so you can't hear the shape of a number field. But the smallest example is degree 7, so it's not that small. And of course, I encourage you to click on links and just browse the LMFDB and see where you get. Here's an example of how you can use both Magma and the LMFDB to do some research. So here we talked about how primes factor in number fields. And suppose you want to investigate this distribution. The LMFDB pages give you Magma code. So for example, here, this Magma code was just pasted from the LMFDB page for some degree 5 extension. So you can get the number field that you're interested in and just compute things in Magma that didn't appear on the LMFDB. So in this instance, I'm just checking the factorization of primes up to some bound. Here, I'm just counting the number of primes that are totally split, like factor completely in this, like to 5 different primes in this number field, and checking their proportion. In this case, this is predicted by a theorem by Chibotarev. But this is the natural flow. You have things on the LMFDB, you can query it, you can see things there. Sometimes you want to compute beyond that. For that, you can use other computational tools such as Magma to get the things that you're after. Okay, maybe a brief summary. Number fields are governed by some invariants. I don't know if small set is precise, but today we're just touching a small set of invariants, like the class group, the unit group, the discriminant. Kronecker-Weber tells us that a billion extensions of Q live inside cyclotomic fields, and the conductor identifies the optimal one. You can use Magma to compute the conductor. You can use it to compute the Gauss sums that generate these. You can use it to compute class groups and unit groups. We talked a little bit about the Cohen-Lenstra heuristics, which give you open conjectures that you can test pretty easily with Magma and LMFDB, but they're difficult to prove. So, and the Hilbert class field packages what we know about the class group into a field extension, and this relates CM theory and elliptic curves. So tomorrow we will talk about elliptic curves. We will relate a little bit to what we say today about CM theory and explicit class field theory for imaginary quadratic fields.